Hello, everybody. I hope you are doing good today. We are going to start getting into um, climate change. So remember that on this week here, I guess what was this week 5? I believe so. So we're on chapter 14 review sheet, okay, which is due on Sunday, and then you have your current event 4 that's due on Wednesday. And I think I've got everybody a couple assignments graded for you. Um, so everybody should have a current event done and a chapter review. I'm slowly getting to it. I'm sorry. This is new for me as well. I've never taught online classes. I'm trying to get a little bit organized, so I'll try to pick up my game as best as I can for you guys. All right. I don't want to leave you hanging. If you have any questions too, just let me know, and I will be glad to help you out. All right. And don't forget that next week we're not doing a current event. I'm going to actually, Crazy Town. It's not Crazy Town. It's Crazy Town. I want you to listen to a podcast um, next week called Crazy. It's the website, the podcast called Crazy Town. But here's the link to it at the Post Carbon Institute. All right. One of my favorite places, a think tank, are talking about how we're going to live without carbon. And it is called Punching Ronnie in the Mouth, episode 2. All right. Because that week we are going to go back to chapter 5 and talk about economics and sustainability. And this kind of talks about it. All right. Because it was during Ronald Reagan's time that we really started changing our economic, not completely, but we started concentrating on growth a lot more during the Reagan era. All right, we really haven't let that go. All right, there was a pretty pivotal. If you study the history of economics, it was a pretty pivotal um, moment in time. And then the next time, we're also going to listen to this 1.21 gigawatts, and then we're also going to listen to solar freaking roadways when we talk about non-renewable fuel and then renewable energies. All right. So we're going to have a couple of these podcasts. So just keep that in mind next week. It's not a current event, but a podcast. Okay. What else? I don't think that's anything else I need to mention on Blackboard. I'll put up week 7 here for you after I'm done recording this, maybe later tonight during the debate. I hope everybody's going to watch the debate and everybody's prepared to vote. All right. That's all I have to say about that. So let's get into climate change. So, last semester when I started teaching this class was in this class, and Australia was on fire. I mean, that whole continent was ablaze, and then we had the COVID thing. And now we still have COVID, and now California's on fire. And I saw that the wineries out there that the Ringlis and Napa Valley wineries have been damaged and destroyed in the 2002 fires. So there's a growing list of these wineries that are, just ablaze. And I used to always say, climate change. If something happens to, we'll talk about the Gulf Stream, and that Gulf Stream, which is carries all that warmth to Europe, shuts down due to climate change, which it can. And we'll talk about that. There's not going to be any French wine for you, right? No French wine for you. And now I turn on the TV and I see California's wineries ablaze due to climate change. And this is definitely exacerbated. It's not due to climate change, but it is definitely exacerbated because of climate change. And what I mean by that, it's a lot drier, a lot less water, and it's a lot hotter. And things, it makes the fires worse. All right, just like it makes hurricanes worse. Okay, we need to do something about that because you'll see as you progress, and you might have always seen, there's always these climate deniers saying, "Hey, things aren't right." It's just all the way Mother Nature is. The changing of the seasons. All right, we have a president who has literally said it's a Chinese hoax. Okay, and that just drives me crazy. This website right here is called Skeptical Science. And this is, a critical thinking website, in my humble opinion. So if you ever have a question about somebody, not only about climate or whatever, about science, and you're wondering if something's true or not, go to Skeptical Science and put it in their search engine, all right, and something will pop up. But this is one of the best ones I use for climate denialism, all right, because it lays down the facts. And one of the things you're going to hear is that some people will say that the climate models weren't right. And we'll talk about what a climate model is in a little bit more depth. But a climate model just is a linear regression model where we know the temperature. We want to figure out what the effect of all the things going on in the Earth, how that affects the temperature. All right. So we have temperature on the right hand side of the equation is the independent or excuse me, the dependent variable. All right. And that is a function of all these other things. So the temperature of the Earth is a function of how much snow we have on the ground up there in the Antarctic, how much greenhouse gases we have in the atmosphere, how much ocean water we have, how much of that ocean water is covered by ice caps, right? Yes, how far we are from the sun, what the tilt of the axis is. So all these variables are going on in there. And since we know what those variables were in the past, we can put them in that model and then project with some type of certainty, sometimes 95 to 99% certainty, depending on what we're trying to do with these models. The more important the model, the more certainty we want to have. As medicine, we want to be 99% sure, right? But I'm an economics guy, so I can get away with 75%. Okay, so but these climate scientists are 99% confident in a lot of their models, and they were spot on. All right. So I want to watch this little uh, video here about these climate models. All right. And if we would have listened to James Hansen a long time ago in 1986 when he testified on the floor of Congress about climate change, we would be a lot better off. All right. But he was basically laughed off the stage, laughed out of the halls of Congress. And it was a shame. All right. So let's watch this little bit of a video about the climate models and how precise they actually were, because they called these forest fires, they've called these droughts, they've called these bigger hurricanes. This red is the actuals, and this is his model, the blue. Yeah, that's probably one of the most famous, James Hansen. And the red is what happened, and then these are his two different models, and he was spot on. That's the one you guys hear all about, the IPCC with the Paris Accord, and all the nations got together. And James Hansen's a part of that. All the scientists get together to do this. This is a global thing. It's very important. This impossible expectations. I hear people do that all the time. And you got to, we're never going to get rid of lead in the atmosphere or lead in the world, right? No, they're not. So these are the guys that the deniers. We can look at their models and we can look at the other models and we can see who was right. It's not rocket science. Okay, this is adding and subtracting and looking at past data. What has happened in the past, and we are smart enough to figure it out. All right. So if you ever hear anybody talk about global warming not being real or whatever, just I don't know what to say. I try to talk to them and try to convince them, not convince them, but just try to, I guess I should say, educate them. But it's a uh, hard nut to crack, right? These some of these people just don't want to listen to reason, all right? So just brush it off and do your part to help out this world, all right? And if you ever have a question about science, uh, use this website, Skeptical Science, and they'll answer just about almost everything, all right? Even one of my questions, you want to prove me wrong, go ahead, go to there. I need to know, all right? That's one of my favorite websites, okay? So let's get into climate change. And I may, folks, actually do this in three different sections just to keep it to like a 20 to half an hour viewing instead of doing like 245, because this is kind of a longer section because it's an important one. Because we've talked a lot about how man has, environmental science is the um, study of the environment and humanity's place in it and effect on it, right? And it is amazing that we have been able to affect the climate as well. We've changed every single biome, and now we're starting to affect the climate. And it is definitely anthropogenic. It's definitely man-made. Okay. But in this lecture, we're going to talk about the Earth's climate. And the Earth's climate is very dynamic, and there's a lot of natural factors. And we do not want to ignore those natural factors. We want to include them in our models. Okay, so we'll talk about all the different factors that influence the global climate, greenhouse gases, humans' influence on climates, the methods of climate research, current and expected impacts of climate change, and ways to respond to climate change. My favorite topic. All right. So the case study for this class or this section was the rising seas threaten South Florida, and boy, I'm telling you, South Florida is definitely in trouble. Miami, not Miami, but is it Miami? I think it is Miami. That is like flooding when it's sunny out, right? And that's just due to rising tides because there's more water in the ocean. Okay, they're already in trouble. You can see this guy having to ride his bike right through the flooded streets here. All right, so at least 6 times a year, salt water intrusion will bubble up from the ground and flood the streets and sidewalks of Miami Beach, being the most effective. So you'd be sitting there, and all of a sudden, it's not raining or anything. It's just that there's kind of like the ocean motion, the motion of the ocean brings that water into shore a little bit, and it kind of bubbles up, percolates from underneath. Okay, and the floods are related to new phenomenon as a result of rising sea levels caused by global climate change. And it's not only, I'll put a little aside here, it's not only the rising sea levels that we're finding in Miami, but Norfolk, Virginia, which is our biggest naval base, is actually sinking, all right, while it's rising. Okay, because if you think about the sand, Florida is built on limestone, so it doesn't sink as much. But Norfolk has a lot more sandy loam soil out there, and just think about it as the water comes in and you pour water on your sandcastle, right? It flattens it, right? And that's what's happening. The water's coming in and kind of taking out some of those air bubbles that the land's on, and air bubbles and just sinking the land. So it's not only sinking rising tides, it's also sinking land in some areas. Okay, so the world's oceans rose more than 20 centimeters in the 20th century as warming temperatures expanded seawater. All right, so because we've got to remember scientific, experiment you can do when you heat up water. Guess what? It expands. Okay, so it's not only rising because we're adding more water to the oceans, but it's getting hotter, causing those molecules in that water to expand. Um, and also the melting of the glacier of ice. All right, so all coastal cities are facing challenges from the flooding of increased storms. It's all over the place. South Florida is not alone, but it's estimated that Miami has spent over 40 billion of assets located just meters from the ocean. All right, so they just meters from the ocean. They got 40 billion on these skyscrapers here. All right, so 6 times a year, these skyscrapers are getting flooded on sunny days. Could you imagine the amount of money? We're lucky that here in the United States, in Miami, has the money to put in the infrastructure to pump that water out. Right? They're having a tough time keeping up with it, folks. All right, but at least we have the technology and money to do it. Other nations, we talked about environmental justice in chapter 1. Other nations don't have that ability, and what's going to happen to them? Okay, they're just going to have to live in a foot of water, I guess. Despite these challenges, Miami Beach is currently undergoing a building boom. All right, we're still building down there, and its state levels leaders are largely in denial about climate change. They're starting to change their minds because they're seeing it, but some of the representatives there are not really stepping up to the plate to do what they really need to help with climate change. Not just the technology, but more or less, in my humble opinion, of changing people's attitudes. Some of these people just got to wise up and admit that it's not a Chinese hoax. Okay? So the local leaders who see it right in front of us are working hard to try to do things. Okay? Because it's their home. Okay? Our dynamic climate. So climate is definitely dynamic, meaning there's a lot of different variables that enter into the evaluation of the climate. All right, and what impacts it. All right, so we have temperature, we have precipitation, the wind, the humidity, barometric pressure of how much the air is weighing down on us, and solar radiation, how much sun we're actually getting to the earth. All these factors are in those models, all right? And we can try to figure out, we take this one and make this the dependent variable, and all these the independent variables. If we want to figure out the wind, we make this the dependent variable, and all these the independent variables. Make sense? All right, so all these are interrelated, and depending on what we want to figure out, we can. All right? Global climate change generally refers to climate change. Okay, and it describes changes in temperature, precipitation, and frequency intensity of storms across the world. So you got to remember climate change and global warming are two different things. All right, global warming is just those models looking at the temperature as the dependent variable. Okay, and that can either go up or down depending on all these different kinds of factors. All right. But when we look at global climate change, we're looking at all these different things and seeing how they work. All right, so it's more of a, how's the rainfall change? All right, and we know that we make this the dependent variable. Now we look at the independent variables, temperature. What happens when the temperature goes up? What happens to water? It evaporates a little bit more. So that's going to put more water in the atmosphere, causing it to have more precipitation, right? So, climate change there's a lot of different dynamic influences on that, okay? The three factors exert the most influence on the Earth's climate. The sun, which provides all the light and warmth, right? The sun is the primary energy source for this Earth. Without the sun, we would not be around, right? The atmosphere, which prevents major temperature shifts of night and day. So the atmosphere is like our thermostat, right? It controls the greenhouse gases, control basically how much heat is retained during the nighttime, right? And then it's released back out into the atmosphere or whatever, and keeps us nice and warm. If we did not have the atmosphere that we had, we'd be living on an ice cube. Right? We would be just as cold as Mars. That's why Mars doesn't really have warm temperature, because it has no atmosphere. But adversely, if you look at Venus, its atmosphere is full of greenhouse gases, and it's thousands of degrees temperature. We can't live there either, right? And then we also have the oceans, which stores and transports the heat and moisture around the Earth. And it's amazing. We're going to see the oceanic conveyor belt that runs this great distribution of the heat around the Earth. And it's an amazing, amazing thing. Okay? It's a wonderful sight to behold, in my humble opinion. Okay? So the sun applies most of the planet's energy, with the atmosphere absorbing and reflecting most of it before it even reaches the surface. All right. So in our climate models, we are going to put all this. We're going to put the reflective part of the sun in here. So we're going to look at the cloud cover and see how much is actually bouncing off, right, from the clouds. How much actually make it in, right, and then how much is absorbed by the oceans during the daytime, how much is absorbed by the land during the daytime, how much is radiated off and trapped by the greenhouse gases. All these different factors go into regulating the heat, all driven by our ultimate energy source, the sun. So atmospheric gases have 3 or more atoms in molecules that tend to absorb infrared radiation given off by the Earth's surface and emitted down backwards. Okay? And these are basically called greenhouse gases. And these are the ones that regulate the temperature of the Earth. Okay? They store the sun's heat during the day and keep us warm during the night. And we have a couple of different ones: water vapor, ozone, carbon dioxide, nitric oxide, methane, and halocarbons. All right? All these are like water vapor is basically a natural source, but we are increasing the water vapor, like I said, because it's getting hotter and more heat is out there. The bigger the more evaporation you're going to have. Ozone, we don't control this, but we can break this ozone down. All right, we'll talk a little bit about it, the ozone layer, and what was once was known as the I can't remember the name. The Montreal Protocol. Right, which was a time in history during the Reagan era, believe it or not. Actually, it was Bush Sr. that signed it into law, but we got it together during the Reagan era because the ozone was getting a big, huge hole in it. When we lose this ozone hole, we get cancer, and no one wanted cancer. So the world actually worked together and ban some of these halocarbons and some other things we were releasing from our refrigerators and stuff to stop the depletion of the ozone. All right. Then carbon dioxide, which is the biggest factor that we have today when it comes to climate change, right, is man's constantly putting out this CO2 into the atmosphere, and that's a greenhouse gas. All right, nitrogen oxide, methane. Also, we also contribute to this, but a lot of this is also done naturally. Okay, so what we have to try to do is try to bring down all our effects, what we're affecting humanity's addition to these, because some of these things are natural. All right, and it's always been a natural cycle. We've always had about 350, 280 to 350 parts per million of in the atmosphere when humanity was growing up to be humanity. And now, folks, we have 410. So we've never been around to see this result of having so much carbon dioxide in the atmosphere. The rewarming of the lower atmosphere by emitting infrared energy by these gases is called the greenhouse effect. Okay, and that's what keeps us up there. All right. So here we see on this little chart, we have the greenhouse here, relative heat trapping ability of CO2 equivalents, and over 20 in 1 year. So carbon dioxide is a one-to-one effect. All right, but these are a lot more powerful. So methane, nitric oxide, and hydrochlorofluorins are high, give us a higher global. They trap more heat. All right. They do not last as long. I think the hydrochlorofluorins, I don't think they last as long as CO2. All right. Methane actually turns into CO2. But this is one where actually humanity is most responsible for. But we may have a positive feedback loop in the methane emissions here, and we'll talk about that as we go through this presentation. Okay? But we can see here we have another J curve showing up. And like I say, every time you see a J curve, what I try to do is stop and look, right? Because something is happening. And that could be good or that could be bad. You know, I love to see these J curves in my stock portfolio. Okay, my Tesla this year went woo crazy, all right? But it's up there, and I'm scared it's gonna come crashing down, all right? Um, but this is a little bit different. This is science, and this shows that our carbon dioxide levels since beginning of time to 2000 has just grown right here into this exponential, the beginning of the Industrial Revolution, right? Us starting to use fossil fuels on a regular basis, right? And that's what we did. We just pumped it out, right? I mean, my grandfather is 101 years old, and he's not doing too well. So I don't know how much longer he'll be around. But when I think about it, he was actually born when this was starting to turn crazy, right? Yeah, he was probably born right here in 1920, right? So probably right here in this J curve. But he lived through this whole area of our fossil fuel use, of us just consuming more and more fossil fuels. It's amazing to just for me to think about that, right? What a wonderful person. He's lived a very very good life. Okay. And you can see here also that our methane, our nitrous oxide, and our methane, this yellow one, is also starting to turn up. All right, and this is all anthropogenic generated. We can calculate how much CO2 we are adding to the atmosphere. All right, we have that ability to do that math. All right, we are not idiots, I should say. Okay, makes sense? All right. So the greenhouse gas concentrates are rising fast, and it's basically due to our combustions of fossil fuels, transferring carbon from one reserve underground deposit to another reserve. Okay. So you can see here the plants would take in the carbon dioxide through photosynthesis, put it in their trunks, and then they would fall over and turn into coal. Right? Or they will let some go out in respiration. Okay. into the atmosphere. And the sun and the oceans do the same thing. All right, the algae would absorb it, and some will go down on the bottom of the ocean for oil later, and some will be released into the atmosphere. Okay, but it was a natural uh, flow of that carbon cycle that we talked about in chapter 2, I believe. All right, so we had that natural flow, and some of that carbon was still emitted from volcanoes and things like that. But then all of a sudden we started doing some industry, all right, and we started taking out all this stuff that was reserved, absorbed by the earth and sequestered deep inside the bowels of our earth there, and started releasing and increasing the amount of CO2 in the atmosphere, the amount of balloons available to add heat to regulate our environment, our little temperature of the earth. Okay. And we definitely are smart enough to be able to calculate that and see that we are actually adding. We've gone from, like I said, about 280 parts per million to 410 parts per million in a blink of an eye. All right, because there used to be a time when the trees used to take back everything we put out. Right, that is not happening anymore. I think this is the first year, or maybe last year was the first year that the Amazon rainforest was not actually a carbon sink. It was not. It was releasing more carbon from burning, the fires burning, than it was actually sequestering carbon with all those trees. All right, and that is a tipping point that the climate scientists have talked about back in 1986. All right, it's time we listen to them because we know what they have done is pretty darn spot on. All right, we can't have great expectations. All right, but they have been definitely close. All right, and they've been honest about what they are actually doing too. They don't try to hide that their model is only this or that. All right, they tell you exactly what is in it and how they came up to that conclusion. All right. But there's a lot of other factors than just the greenhouse gases. But that's the one we're mostly concerned about when it comes to global warming and human-caused global warming. But like I said, there's a lot of natural stuff out there too, and other things that cause the temperatures to change. So aerosols are microscopic droplets that can have either a warming or a cooling effect when present in the atmosphere. So there's soot particles, that black carbon aerosols, cause warming by absorbing solar energy. Right, so if there's black soot going up there, the sun's gonna heat it up. Okay, but most other aerosols like sulfur, we actually reflect solar energy and have a cooling effect. So back in you'll hear sometimes the global warming deniers will talk about how back in the 70s we said that the earth was going to cool, and now look at it, it's all super hot, and they were all wrong, and how can we trust them? But what they were talking about in the 1970s was that we were putting out so much pollution, we were putting out these aerosols that were reflected, would cause the earth to actually get cooler. So we actually put in, plus half the stuff, these aerosols and stuff are pretty dangerous. Okay, it's not too healthy. So we put in some effects to decrease that, and guess what? It worked. All right, and I'm pretty sure everybody still has electricity. All right, if you're taking this class, you still got electricity and never have to worry about it. All right, so we were able to do those kind of things without any big problems per se. Okay. Then there's also radiative forcing, which is the amount of change of thermal energy that a given factor exerts on the Earth's temperature. So a positive forcing warms the surface, and a negative forcing cools it. Right? So when all the factors are considered, the Earth is experiencing a net radiated forcing of 2.3 watts meters squared. All right, so we are forcing the temperature to increase it. I have a positive force of 2.3 watts meters squared. All right, and there's just different little things. So you see surface reflectivity, land use, soot and snow. All right, we're actually decreasing that, right? We're having less, or we have less soot on the snow. If we increase this, it's going to give us more watts per meter squared, right? And you can see our carbon dioxide, we're increasing our carbon dioxide, increasing our nitrous oxide, right? So the total anthropogenic radiant forcing, we add up all these red little bars, right? And then everything we um, release that cools it, all the aerosols that cool it, we can see we're above. We can designate 2.3 extra watts meter squared due to our impact on the environment. Okay? But there's also those natural occurrences for the sun, right? Uh, for climate change, right? So over thousands of years, the Earth wobbles on its axis. We all know that, right? And the tilt changes it, and that experiences different shapes of the orbit, which is called the Milankovitch cycles. And so we'll know, like sometimes that the Earth is going, around here, and then it widens up and a little bit more elliptical. All right, so that's when we're getting the ice ages here, and then we have the warmer periods, and then the ice ages. These happen on relatively thousands of years time scale. We can track this through history, all right, or we can look in the past at least, and then apply that to the present, all right, or project that into the future. If this has happened for millions and millions of years, the same type of rotation, pretty chances are that it's going to keep on happening. All right, and then there's also the tilt. All right, the tilt changes every once in a while. Okay, and it just wobbles. Okay, so those factors are actually put into all of our climate models. Believe it or not, it's just that they don't add as big of an effect on as CO2 has, because we have forced that CO2 out into the atmosphere real fast. And in 100 years, we increased it from 280 to 410. Okay, and the sun, and the Earth traveling around the sun, this takes thousands of years. All right, this is kind of a little bit more incremental. Make sense? So the sun varies the amount of radiation it emits to. So science believe that it has not had a significant effect on the average Earth's temperature, assigning it only a value of about 0.5 watts of radiative forcing. So yes, the sun does change. It gets hotter and cooler. It's usually in about an 11-year cycle, and we watch that all the time and can predict it because we've seen it happen in the past. And one of the interesting things, when the climate scientists say, "Oh no, it's the sun, it's just getting hotter," I'm like, dude, we watch the sun like 24/7, 365. We know exactly what's going on with the sun because it will do these solar flares, and those solar flares come to hit us. That will wipe out like all of our satellites, and then we have no cell phones. Okay, so we watch the sun all the time to look for those solar flares, and when they start coming out, we shut down those satellites real quick. All right, if they're going to strike the satellite, so we can keep our cell phones on. All right, so we watch the sun 24/7, 365, and we would know if it's getting warmer. All right, then there's also the oceans. The oceans hold 50 times more carbon than the atmosphere. All right, but is absorbing less carbon today. It's getting to the point of the law of diminishing returns. All right. And we are in some big trouble with that, okay? Because that carbon dioxide is going to end up in the atmosphere, causing it to warm, okay? But that's just the laws of nature, right? The ocean can only hold so much heat, okay? And you're definitely going to get the laws of diminishing returns, and so can our atmosphere. It's only going to reach an equilibrium eventually, all right? The ocean warms. Gases like CO2 are less soluble, creating a positive feedback loop that accelerates the warming. So, I think it was chapter 2, we talked about that. Why does man create more positive feedback loops than usual? All right, we just keep on adding more and more CO2, causing the acceleration of the warming, right, due to our actions. Then we got what's called the thermocircular circulation of the oceans that moves tropical water north, where the heat is released near Western Europe. And this is probably one of the not missed, I should say, most ignored wonders of the world, in my opinion. The ocean conveyor belt distributes the heat all around the Earth. That Gulf Stream that goes up there. I hope you guys all know about the Gulf Stream and who first monitored the Gulf Stream. Easy answer, Benjamin Franklin. If you ever want to say, just always say Benjamin Franklin. You got a pretty good chance that, he did the eyeglasses, the library, hospitals, all this stuff. Okay, he was kind of the dude, right? But he was the first person to track that. But that important to that Gulf Stream is that it takes all that hot water from the equator and brings it up to Europe, and then the westerly winds blows all that heat onto Europe, making it as hot as it is today. And voila, we got that fine French wine. And believe it or not, that circulation belt can shut down, right? And if it does, they are going to go into another ice age, right? Because the freshwater input from Greenland melting the ice may disrupt this flow. Well, I'll show you a little bit of video after this slide um, to help you understand it a little bit, okay? We also have in the oceans, we have multi-year variabilities that arise from what's called the El Nino. Okay, so this is in the Pacific, and sometimes a lot of the hot water is closer to Asia. Okay, I think that's the El Nino. And then there's El Nina, where the warmer water is more distributed. So when we have the El Nino, where it's all over by Asia, that's when California is getting really dry, right? And they're having their droughts. Okay, and this too, just like the sun has that 11-year cycle, there's like a 7 to 11-year cycle with this El Nino and El Nina effect of the Pacific Oceans. And it's been around forever. This is actually first was documented by, I think it was the Peruvian Indians way back when. Those guys that made all those little pyramids back then, right? They were watching the cycles of the El Nino, and they were writing down the weather. And they would say, hey, we've had this drought going on for 7 years. Hey, it's been really rainy for 7 years. And that's when we picked up, hey, they were noticing the El Nino effect before, too. So these shifts have been around forever. And there's a lot of these different little tiny ecological environmental things that happen close to large bodies of water, right? Where there's kind of shifts in even the Great Lakes areas, okay? Due to the waters being a little bit warmer. I guess you call it the lake effect snow, right? Since the water's a little bit warmer on Lake Erie in the beginning of the winter, the snow effect is happens a lot because there's a lot more precipitation happening, right? Okay, so let us get out of here so we can have some extra time. So that 20, that's good. Let me show you the video I was talking about with the Great Oceanic Conveyor Belt. This is one of my favorite videos here. I should have brought this up before because I always share this to every class, just about. See if I go. There it is, baby. Got it. All right. So this is a little video from. Let me get rid of this. Thanks. Mute this. I have to wait for this ad to get done here. So this was done by a guy called Al Gore. I don't know if you guys know who he was or who he is, but he is one of the he is one of the leaders in the climate change. We got to do something about it camp. And he went around the world doing these little speeches, and this is one of those speeches he does. But this is a great example of the oceanic conveyor belt. All right, and this thing is just amazing to me how nature has been able to do this. So let's watch how this works, and then notice. I mean, this couldn't be a positive feedback loop at the end. It's going to be a negative feedback loop. We'll actually global warming make the world cooler, right? Sometimes I might have commented on some of your guys' papers or homework assignments that the humans have a lot of positive feedback loops. All right, we cause a lot of them, but Mother Nature will fix it for us. All right, usually, and this is one way that Mother Nature would fix this. Okay.
Climate is like a big engine for redistributing heat from the equator to the poles. And it does that by means of ocean currents and wind currents. They tell us, the scientists do, that the Earth's climate is a nonlinear system, just a fancy way they have of saying that the changes are not all just gradual. Some of them come sudden in big jumps. On a worldwide basis, the annual average temperature is about 58 degrees Fahrenheit. If we have an increase of 5 degrees, which is on the low end of the projections, look at how that translates globally. That means an increase of only 1 degree at the equator, but more than 12 degrees at the pole. And so all those wind and ocean current patterns that have formed since the last ice age and have been relatively stable, they're all up in the air, and they change.
And we don't, scientists don't really know too much about
A
that.
lot of time studying the
So the scientists don't know too much about all these wind patterns. Well, they know about these wind patterns. They don't know what's going to happen. This is one of the hardest things for them to predict. All right, and you might have noticed a couple of times we've had these really cold winters. All right, and they have these, the cold air is blowing down from the north. All right, and that's because it's jet streams. One of the jet streams that goes across here is weakening. All right, and there's some hot water here from the El Nino pushing up the jet stream up to Alaska. So it's 50 degrees in Alaska in January and negative 20 in Pittsburgh. All right, it's like almost the opposite. Okay, it's just an amazing effect. And science, this is the one thing that scientists, climate scientists, will readily tell you: we don't know what's going on. All right, well, we can't predict exactly what's going to happen. We can tell you what's going on. The jet stream weakening, and this whole heat mass is going up here, and that, but they can't really have a good model. They can model how the temperature is going to rise, but it's hard for them to model where the wind's going to blow. Okay.
worried about, where they spent a lot of time studying the problem, is in the North Atlantic, where the Gulf Stream comes up and meets the cold winds coming off the Arctic over Greenland, and that evaporates the heat out of the Gulf Stream, and the steam is carried over to Western Europe by the prevailing winds and Earth's rotation. But isn't it interesting that the whole ocean current system is
Look at that
almost
thing. It's
completely
amazing.
loose?
I mean, that thing's been chugging along, just chugging along. And here's the Gulf,
The red are the
and here's the Gulf Stream, right? That Ben Franklin tracked, right? And you can see the warm air up here just blowing across Europe. And it's about the same temperature as, it's way up here in Canada, but it has the same temperature as Pittsburgh. And that's because of this warm air, right? This loop, this conveyor belt. All the cold air comes out, cold water comes here, and it comes back up here, gets all warmed up, and blows off here, and cools down here. It's just an amazing system. Right? The Earth,
the
can't
orange is the best known,
blows me away.
but the blue represent the cold currents running in the opposite direction. And we don't see them at all because they run along the bottom of the ocean. Up in the North Atlantic, after that heat is pulled out, what's left behind is colder water and saltier water, because the salt doesn't go anywhere. And so that makes it denser and heavier. And so that cold, dense, heavy water sinks at the rate of 5 billion gallons per second.
Imagine 5 billion
And it
gallons per
pulls that
second.
current back south.
That's a
At the end of
riptide.
the last ice age, as the last glacier was receding from North America, the ice melted and a giant pool of fresh water formed in North America. And the Great Lakes are the remnants of that huge lake. An ice dam on the eastern border formed, and one day it broke. And all that fresh water came rushing out, ripping open the St. Lawrence there, and it diluted the salty, dense, cold water, made it fresher and lighter, so it stopped sinking, and that pump shut off.
Shut off.
And the heat transfer stopped. And Europe went back into an ice age for another 900 to 1,000 years. And the change from conditions like we have here today to an ice age took place in perhaps as little as 10 years' time. So that's a sudden jump. Now, of course, that's not going to happen again, because the glaciers of North America are not there. And is there any other big chunk of ice anywhere near there?
Yeah, so what he's saying is scientists say if some of this water here or ice here melts, it turns into water, fresh water, it will dilute this, make it less saltier, and shut down the conveyor belt like it did when the St. Louis opened up and poured that stuff out. All right. Do we know what's going to happen? If this will happen? No, we don't know if this is going to happen. Okay. And the scientists are clear about that. And it's not going to happen like it does in the Day After Tomorrow movie, I think that's called. Okay, that was a little bit too fast, but 10 years is a fast time, right? And you saw, how where Europe is on the longitude and latitude points. I mean, it should already be icy. Okay, and if it wasn't for this conveyor belt, Europe would be a totally different place. I mean, no French wine for you. All right, no California wine because we've got the fires going on the other side. I mean, better stock up. If you're 21, go out and buy some. Okay. All right, so let us stop here. And like I said, I'll probably do 3 videos on this because this is a longer thing. We'll see how the next presentation goes. All right. So if you guys have any questions, let me know. And if not, have a good day and keep working hard, everybody. Okay.